All right, so again, like overall, you've had some graphs that had really nice distributions and you could get a lot of information from it. But sometimes, especially if my data set is really large, like if I survey the entire population of the United States, it would suck to actually plot in each individual responses. So instead, we come up with a frequency distribution and we look at it as terms of either groups of classes, or we look at it as groups of how many times this response has occurred, or this range of responses have occurred. So that way it's a little bit easier to actually see what's happening in your data, and you don't have to sort through a million responses on that data set. So today, the only thing that we're going to talk about, or the big idea, the big picture, is to talk about these frequencies that are occurring. And again, we use it for a big data set that we have. So it's a chart general that pairs this value with its frequency, and we've got a couple different ways that we can pair our value with its frequency. One is an ungrouped frequency distribution, which assigns each x value the number of times that happen, and that stands alone. And sometimes this is a better idea to do and come up with a frequency that each of these things happens. Like if I was rolling a dice 1,000 times, the responses that I get of my dice roll are 1 through 6. So I'm only getting 6 different things. So it makes sense to have each x value stand alone. And then I record, 3 happened 200 times, and 4 happened 317 times, and whatever. Okay? But if I'm getting a lot of responses back out in my big data set, I would probably group it in some distribution, so that way in a certain class, and look at a range of scores, and so I can see patterns a little bit better. For example, sometimes they have really natural divides, the ages are a good one to group particular data sets. If I'm talking about a 21-year-old and a 22-year-old, there's not a ton of difference from that. So maybe I want to talk about the 20s, people in their 20s, or people in their 30s, or people in their 40s. And that's a natural divide for those things. Or grades is something like that too, getting an A or a B or a C. Those are natural divides in our data set. So it makes sense to just look at all the B people and look at all the C people. Does that make sense? I don't really care about an 87 or an 88. I do care about B's though. So there can be some places, especially if I'm getting a ton of data, then I can separate it in those chunks, and that way I can look at an entire group. Okay? So that's the main difference for today, is that we're looking at frequency, but there's different ways that we can represent those frequency diagrams. The first thing that we look at is a histogram, which that is just basically a bar graph of that. So for example, if I had this survey of Roman Catholic nuns, blah, 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 and we were looking at different ages and the frequency that it occurred. Again, this is kind of a natural divide where I'm going and looking at 20 to 30-year-olds, or 20 to 29-year-olds, and 30 to 39-year-olds, and so on and so forth. And I'm coming up with a frequency of that actually occurring, how many nuns would be in that age range. Okay? There's a couple things that you have to point out or look at when you're talking about a frequency diagram or a frequency chart, for example, or for instance. You want your width. If you're coming up with a class, if you're coming up with a range of values, you want to make sure that that is even throughout. So each of these are a group of 10. So that makes, that again is kind of a natural divide for this data. But you also want to make sure that you're not double counting something. So in this part, we're including 20 on this side, this left endpoint, but then we go up to 30, but we don't include 30, that goes with the next bunch. So if I had 30 in my data set, I wouldn't double count it in each of these ranges. It would fall between the 30 and 40. Now, ages are a little bit different because those are more discrete values, 27, 28, 29, 30. But what they're saying is you could have a 29.7-year-old, and that would still fall in this range. You would count in that frequency. Okay, yep.
Are you supposed to be recording right now?
Yeah.
Are you recording right now?
Yeah.
Oh. Rare.
After we come up with our frequency that these things are occurring, We can do a couple different things with it. One of the things is we can make some sort of histogram that goes along with that, and it represents the width that we have. So our width again is 10. So when we draw our bar that would go on our graph, we would make that bar span 10 units from 20 to 30. And then again, the other thing that you want to make sure is that we don't like double count. So again, like histogram, it's just a bar graph. So that's not different from yesterday. There's only like one tiny little shift, is that we use it for those grouped frequencies, so that we're looking at the bar between 20 and 30-year-olds, or 40 and 50%, and 50 and 60%, as long as you don't double count. Does that make sense? You're going to end up writing on this, so you can use that. Okay, any questions so far? So if I took this data set and I created a histogram that goes along with it, again, along the y-axis is really the number of times it's occurring, like a bar graph, and we have our age ranges, or our bars going between 20 and 30. So yesterday when we did our bar graph, it was like on the actual like category that we did. This is between two particular ages. That represents the class size that we have. So a couple questions came up in first hour. Someone said, like, what if we had a bar graph, like this histogram, but we had like a lot of times you might see data where it's like all in this nice little order, but then it says like 90 plus or something like that. That happens sometimes with data sets because we might have like really weird outliers. But in general, when we come up with our histograms and we represent our data, we want to make sure that it's even throughout. So you don't do like the 90 plus or the 24 plus or whatever it ends up being. Like, we want to just, it'll all fall into these categories. And that might mean that you have 0 here, but then you have 1 at that frequency. You would just represent it, same thing with your bar in that sense. Okay? Okay. On the page 59 of your book, when we talked about this yesterday, we brushed on types of distributions and how data behaves and the spread of data for those things. And there was a bunch of different pictures for the shape of the distribution. So if you didn't like draw in those shapes, this would be a good time to do that and make sure that you have your shapes drawn. It's on page 59 if you don't get it all done today, but we'll go over the 6 main shapes that we have for our distribution. So this actually would fall into a particular shape, and we're going to see that in a second. But in general, when we talk about distributions and we talk about how data is arranged, we mention what that like actual histogram looks like, and it tells you information about how your data is behaving. So one of the ways that you can have your data behave or data arranged is a symmetrical graph. And that symmetrical, sometimes these kind of overlap a little bit, like symmetrical graphs are also normal, also uniform. But in general, if it's the most basic, we can say that it's symmetric, meaning that it's identical on either side. Again, there's lots of different ways that something can be symmetric. This is one way, but it would be symmetric about the middle, and have a mound in the middle, and it's go off on either side. A lot of your data is actually arranged this way. Like if you ask for a variety of responses, data might look that way, especially if you know that you're expecting some mean. But also there are other ways that you can arrange or other ways your data can look. And I mentioned this one yesterday, an even distribution or uniform. Like if I gave a test and I had the same number of A's, B's, C's, D's, and A's that went along, did I say that one already? X maybe, that went along with our spread, you'd end up with a even distribution. So these are like purely, it would be a symmetric, or purely to get the actual representation of a uniform or even distribution, you would have to have the exact number of frequency for each of your categories. But in reality, that doesn't really happen, because when we survey or we collect data, we are dealing with a lot of different variables. And so we just use these as descriptions for a graph. We may say like something looks even though it's not exactly even. That allows us to get a visual picture of what that actually means for our data. Okay? Again, like even or uniform distributions are also symmetric. So some of these overlap a little bit, but we want to use the best descriptor possible. We also have cases like the none example is with some of our data is skewed, and it's a little bit backwards in what you would think as far as the names go. So in this first one, the one that is skewed to the left, most of our data, or we have a big chunk of data that's like pushed in this direction. Like we have a lot of data and our highest is actually to the right. So you might think that that's actually skewed to the right because a lot of our data is pushing that way. But the name actually goes with the longer tail. And the tail are the end pieces, the extreme parts of our data collection. So this is a bigger tail than this tiny little tail on this side. So it goes with the bigger spread that we have. So this tiny little tail on this side onto the right, that one little bar would be a really small tail. So we say that the longer tail is actually the left tail, so it's skewed to the left. Kind of backwards than what you would think. Especially if you're bad with right and left, like me. Sometimes have a hard time and get these mixed up because I want to say that it's skewed to the right. Even if I'm meaning that side, it's just because I can't tell my right and left apart, which I know is like a really sad thing as a 26-year-old person that I can't tell that. But I think it's genetic. My mom's really bad at it too, so I blame my mom. Gotta blame your parents for something, right? She gave me lots of good traits, but that was a bad one that she passed on. On the other side, if our data is like pushed more this way, pushed more to the left, we have a bigger tail on the right. Our right-hand tail is larger. Most of our data falls within our right-hand tail. Our left-hand tail is really small, so it's skewed to the right because we have a bigger right-hand tail. Okay? Those ones are the most common to mix up. Now the only difference between a skew data set and a J-shaped data set is that we are missing this little box here in the corner, like that small tail to the right or the small tail to the left. J-shapes start or end with your highest frequency box. So all of your data is strictly decreasing or strictly increasing, or not necessarily in that same way, but you don't actually go back down ever. Your extremes are actually the high point or the low point. So I'm going to go back to the none example in a second, and so that we can actually name that data set of how that actually describes. We also don't have we don't say that this is a J-shape that's skewed left or skewed right. We just say it's J-shaped. The skewed only occurs if we are naming the tail that we have. Since these are absent of the right-hand tail or left-hand tail, we don't have a skewed part for it. Okay? So if I go back to the none example, we have data, again, that's kind of pushed this way, pushed to the right. Our right-hand tail is small, like most of our data is actually in our left-hand tail, so this data set would be described as skewed left. Okay? Bigger left-hand tail. Does that make sense? Cool. Okay, and then the other two that we have that could potentially be a descriptor of what our data set looks like, and I mentioned this first one yesterday, a bimodal set. If I gave a test and I had, 18 people get a C or a D maybe, 64-ish, and then I had 10 people get an 88, then I'd have something that's a bimodal data set. I have a big group that's in the D range and a big group that's in the B range, and not many Cs. So it's two kind of mounds of data that's collected on either end, and then in the middle, in between those, we have a really sparse data set. Something that's separated by an infrequent section. And the last one is a normal distribution, which you've probably heard that term before. For now, what we're going to say is normal is something that is symmetric, obviously. This thing looks symmetric, and the bimodal could be symmetric too, but normal distributions are always symmetric. And all of our data, or most of our data, is mounded about the mean. which means like most of our data is in the middle. And then we have really sparse tails. As we go out to either extreme, it gets less and less and less and less frequent. Again, for now, that's what we're going to talk about is normal, but we'll learn later on that we have really different classifications for what normal data is actually, or to classify it as normal, we have to have our particular criteria. And a lot of times, things that you go collect in nature, like if I went out and collected a bunch of data, most of my data would actually appear normal. So that's why normal distributions are really important. Most things just fall into a normal distribution where things are surrounded by the mean, where I have a lot of data that's in the middle, and then I have really like few data that's on either end. Okay. Which is why a lot of times if I went and collected a bunch of data, I might assume that that data is behaving normally, and then I can actually see if something actually is an outlier or not, or if it should be considered as part of our data set. There are different statistical classifications for all those things, and to do that, we have to look at what kind of normal distributions look like. So normal distribution is really important, but for now, just kind of know what it in general looks like. It's a bell curve, if you heard that before too. Okay? Okay. So let's pretend that we have a bunch of data, and we're going to do the same thing that we did yesterday, which means that we're coming up with that like percentage, that frequency that something's occurring. We did the count yesterday, and then we came up with the percentage that count was of our whole total data, and then we came up with the cumulative frequency. So part of what we're going to do today is create a cumulative frequency chart, which goes along with the next graph that we do. So we're going to be doing a Pareto type graph that was for qualitative. We're going to do that for quantitative, and that same type of graph that shows the cumulative frequency is called an ogive. So if I gave you some data about whatever, you don't really necessarily have to write any of this down. I just want to go through an example of what you would actually do, and then we'll go over the example of the supplement sheet that you have. We're going to come up with a grouped cumulative frequency chart. Grouped means that we're coming up with different classes for our data set. So groups of or ranges of data that would fall within that, and we count how many would fall within that range. Sometime again, like those groups are really natural dividers, like A's, B's, C's, and D's, or 30s, 40s, 50s, 60s. This one, not so obvious, right? Like we don't really know what this data even is, so we can't really come up with natural dividers. So if that's the case, most of the time I'll just give you a divider. I'll tell you construct it with a frequency or a group of 1 or something like that. For whatever reason, we're coming up with these class boundaries and starting at 3.7. I don't really have a good reason for that, but for whatever reason, this is what that we've decided should be our starting point, and then our width of each of our groups is going to be 1 unit. Okay, so we would go through our list. We'd come up with all the values that were between these two. Be careful not to double count 4.7. So if 4.7 does occur, we'd actually include it into this one. And we come up with a frequency that happens. Okay. Again, not super important that you write any of this down. Just see how this works, because we'll do the same thing on this sheet. Once we come up with our frequency, we definitely need the number of total numbers that we have in our data set, which we can do by counting all those or by just adding up the frequency that it occurs. And we can come up with our relative frequency, which is what we did yesterday. We took our number over the total. We represented it yesterday as a percentage, but today we're just going to use it as a decimal. That's in general how we represent our frequency, our relative frequency, and our cumulative frequency. And then same thing, we come up with our cumulative frequency by adding all of the things that we have down the list. Okay? Now yesterday we did that Pareto diagram, and we plotted our line graphs for that. Same idea, the ogive that we're going to learn next is the line graph of the Pareto diagram, basically. And it's for our our quantitative data sets, and we have our numbers that are included. Okay? Does that make sense so far? Okay. So if I was creating an ogive, it's just a line graph of the cumulative frequency. But there's some key things that you can do to help yourself with the ogive, because you want to make sure that you're not plotting some things wrong. Just like the Pareto diagram, we had some steps to follow. So this is the first thing that you do when you come up with your relative frequency and your cumulative frequency chart. We want to always start with the lower class boundary at 0. Because we know at the lowest that we have, if I'm going from 0 to 4 or something, at 0, I have a 0% chance that 0% of my data is in that range. And then again, cumulative means that we're adding up all of our stuff. We want to represent all of our data. So at the end, the upper class of our boundary, the last point that we're going to plot, has to be at 100%. Or in our case, when we do decimals, it's 0 and 1. If you plot those first, 0, 0, or whatever it is, 0, and whatever your end is at 100, then every point that you plot in will just fall into place. Again, the ogive is like the Pareto diagram, but we don't have the bar graphs that go along with it. We only have the line graphs for it. So we're going to go over one example for the ogive. Again, it's kind of like the new graph, like histogram, it's just bar graph. The only difference is that you have to make sure that it's in that range. So that's on that sheet of that data set. So what I want you to do at the top, because it just has the classes and it has the frequency, so make a column that would be the relative frequency, just like the percent. And then make a column for the cumulative frequency at the top of that sheet. So that's what we're going to end up doing. Okay, so you want to put relative frequency and cumulative frequency. Now they already told us how many exam scores this was. We don't have to count up our frequency. That's great. Or I guess this exam was out of 28 or something, so this must be like some natural divide, I don't know. But they decided that we're going to have widths of 4. And again, when we start out with our ogive, when we come up with our actual plots, our lowest boundary, that's what we were saying, that's what this part was saying, that we should always start with our lower class boundary at 0. At 0, we have 0% of our data. At 28, we should include 100% of our data. So the cumulative frequency is up until that point. Okay? So we can come up with our relative frequency. I'm going to give you a minute to come up with your relative frequency. So if you have a calculator, you can do that. Or it's at a 50, so it's actually pretty easy to calculate in your head what your relative frequency would be. And instead of a percentage, we're going to represent it as a decimal. 3 decimal places. Same as yesterday with 1 decimal place for your percentage. It's the same thing. Which all these ones I think you'll only need 2 decimal places. But if you do have something that's not exact, like these ones will be, use 3. That'd be Instagram, so that is a line graph. Double check your column, you should get this for your relative frequency. And then your cumulative frequency, we're adding those up as we go. What's up?
What's right is that or percent?
So our graph down below is already from 0 to 1. So usually we represent it as a decimal. It's a good question. Not that it really matters, but for our graph and our purposes. And our relative frequency, we'd start here at 0.8, and then we'd add them all down, and hopefully we get to 1, which in this case we do, for our cumulative frequency. Because the Ojai and the Pareto diagram are so similar, like the process of it is really close to being the same thing, but the Pareto diagram is different in a couple different ways. One is we have like a bar graph that goes along with it, and we use it for a qualitative set versus a quantitative set. But also remember the Pareto diagram, we ordered it. We put it in like decreasing order. We always started with the most frequent, which in this one would be like this set. We don't order our qualitative or quantitative sets because it doesn't really make sense to do that. Like we want to arrange it on our x-axis from 0 to 28. And so sometimes like when you're looking at it and you're like, I don't remember if I put them in order or not, like this one doesn't make sense to like change up like your x-axis. So you don't order this one because these are actually numbers that we're plotting. Okay? But for like the categories that we have for our Pareto, it doesn't matter what order we like represent our different categories in. If I talk about like the dent or the blemish or the scratch of the like cabinets, that was arbitrary that I made that list to begin with. So we might as well like put it in order. But this one's not arbitrary. Like these numbers actually mean something. Okay, so we don't put this one in order because we have an x-axis that we're constructing. All right. So down below you have a graph for that. We have our test scores along the x-axis. We have a relative frequency along the y. Again, like the first plot that I would point is at our first lower bound, which started at 0, and like it doesn't, I don't know why this one's not really like at the origin, it doesn't really matter, but we would plot that point first, right here, and then we would plot our last point, which should be at 100%. So if you do 0, 0, or the 0% one and the 100% one, then it makes sense what you're actually going to put in the middle. Sometimes people get a little confused. So at 28, that's representing all of our data, so we put that. Which means then at 4, at this like second boundary point, that would be our 0.8, so we plot that number. At 8, we plot the 0.24. And we collect all of our dots. So again, what this means is that from 0 to 4, you can kind of read it off of your graph, that this change that we have in these plotted points represents the amount of data in that section. So if I were looking at, just from a graph, if I didn't actually have my table for that or the cumulative frequency, I could look at 4, at this point I have the 0.24, and then at 8 I plotted 0.4. So I could tell that 0.16 or 16% of my data is in that range from 4 to 8. Or I could tell that at 12, let's see, 40% of my data is below 12. Okay, so you can see that from like our cumulative frequency chart. You can also see like individual relative frequencies to talk about our data in that way. So if I ask you this question, which one's the biggest group? How could you see that graphically on your Ojai? Brandon, what do you think?
Isn't that the biggest difference?
Yeah, the biggest difference. So on our graph, the biggest difference that we see, the biggest jump between our plotted points is this section, the 12 to 16. Does that match up with your count from above? Yeah, that's our biggest group, right? So you can see our biggest group and our biggest difference by like the steepest slope, the biggest jump between your 2 points. Especially if like along the x-axis, which we do have, we have those even widths. So the biggest change in percentages would be there. Okay? And we could say too that would be like looking at our graph between 12 and 16 that we have, it's a 40% jump. So 40% of our data is in that range. Okay? Compass is a big part. Okay, so for your homework tonight, you're using the how long was your longest relationship data part, which is the section on the class set, and you're coming up with the grouped class. and the frequency, relative frequency, and cumulative relative frequency, which is just this chart. This one over here. Woo. This one that you need to create your ogive anyway, so it's kind of all in one question. And then the other thing that you're doing is coming up with the grouped relative frequency histogram. So after you've like come up with your chart for that thing, you can use your data to do your relative frequency histogram, and then the ogive, you can use that same chart. Okay, that's one thing. Like you're creating kind of a couple of graphs with that one data set. You have one more problem to do on page 64, number 37, and then pre-noting 2.3, which is on like mean, median, and mode. It's actually not that long. Okay.